Okay, we're going to solve a problem in equilibrium from Chapter 5. This is Chapter 5, number 3, and the problem states that there is a speaker suspended from a ceiling by two cables. Each cable is 30 degrees from the vertical. So I've sketched the ceiling up here. Here's a box indicating the speaker. These are the two cables, and each one is 30 degrees from the vertical. So this angle is 30 degrees, this angle is 30 degrees. That's equivalent to this angle being 30 degrees and this angle being 30 degrees. Either way you do it, the cable is 30 degrees away from the vertical. And the question is, what is the tension in the cables? We are given that the mass of the speaker is 20 kilograms. So, and that the speaker's suspended, stationary. We're also told that the distance of the speaker from the ceiling is 2 meters. So let's do a free body diagram for the speaker. So the speaker becomes a dot, and then we identify the forces that are acting on it. So what forces do we have on this thing? Well, there's two cables, so each one of those is applying a tension, and we can label them like so. Just for the sake of specificity, let's go ahead and label them as TL and TR, instead of assuming that they're the same right at the moment. So those are the two things that are in contact with the speaker. Since we're on planet Earth, there's an additional force, which is the weight of the speaker. And the weight is given by the mass times the acceleration due to gravity. And those are the only forces acting on it. And because the speaker is in equilibrium, it's not moving, we know that its acceleration is 0. And this tells us that the sum of all the forces acting on it is also 0. And if the sum of all the forces is 0, that means that the sum of all the x components of all the forces is 0, and the sum of all the y components of all the forces is 0. So this vector equation becomes two scalar equations, one in the horizontal and one in the vertical. So we'll go ahead and define our coordinate system in the usual way, with x being horizontal and y being vertical. And now we'll identify the x and y components for each of these forces. I'm going to go back to the free body diagram and put a vertical line here and just remind myself of the angle or the orientation of those two tensions. Now, I made a point of identifying this tension as TL and this tension as TR. Let's go ahead and keep that assumption in place for a second. Now, each of these two equations, sigma fx equals 0 and sigma fy equals 0, where this large Greek sigma just indicates that I'm adding up all of the x components of all the forces. So this represents an equation with a bunch of pieces in it, where each piece in there is the x component of one individual force. So let's identify the x components of all these forces. So what's the x component of TL? I'll call TLx. I look at my force vector up here, and the x component is the piece of that vector that is pointing in the x direction. That'll be TLx here, and TLy is the other perpendicular component of that. So just as a reminder, TLy is entirely in the vertical direction. Head to tail with TLx, which is entirely in the horizontal direction, gives me the vector TL. These are the legs of the right triangle, where the vector is the hypotenuse. Anytime you're asked for the component of a vector, first thing you do is write down the name of that vector, and then it's either the sine or cosine of some angle. for the angle that we're given 30 degrees here, TLX is opposite that. So it's TL times sine of 30 is the x component of L. Now, I've identified my coordinate system with x to the right being positive. TLX points to the left, so I'm going to put a minus sign on that. TRX, the x component of the tension on the right, is also TR sine 30. It's the same right triangle. The only difference is I've called this TR instead of TL, and this one is pointing to the right, which is the positive direction, so that gets no modifier. And the weight is entirely vertical, so the x component of the weight is 0. So I've now identified the x components of all three force vectors. This equation, the sum of Fx equals 0, means TLX plus TLY plus WX equals 0. That means minus TL sine 30 plus TR sine 30 plus 0 equals 0. That then gives me TR equals TL. So we might have guessed that from inspection. The two cables are at exactly the same angle. They must be pulling with the same tension, but I wanted to work through that just very methodically to show you that that information comes out of the vector math and the physical setup and knowing that this thing is in equilibrium. So there's just one tension. TR is equal to TL. Each rope is pulling the same amount, so we'll just call that T going forward. And now we have to look at the Y component of the force vectors to figure out what the magnitude of that tension is. So I have, what are the Y components? TL Y is pointing up. It's TL cosine 30. Sorry, and we're just calling that T cosine 30. And T RY is just T cosine 30 also. And the weight vector is entirely in the y direction, and it's down, so it's negative. So it has a value of minus mg. And the sum of our y vectors then gives us t cosine 30 plus t cosine 30 minus mg equals 0. That's just rewriting this equation here. So that gives me 2t cosine 30 equals mg, which is 20 times 9.8. And we grab the calculator. 20 times 9.8 is 196 newtons. That's equal to 2t cosine 30. That gives me t equals 196 divided by 2 divided by cosine 30. 30 cosine is 0.866 times 2 divided into 196. I goodness, have to start over there. 196 divided by 2 divided by cosine of 30 gives me 113 newtons. So each cable has a tension of 113 newtons. We can do a sanity check on that. That's less than the weight of the speaker, which is 196 newtons, but there's two of them. Each cable is applying that much force. It's more than half the weight, but that's okay because they're not pulling straight up. So if they were pulling straight up, they would each bear exactly half the weight. Since they're at an angle, there's some extra tension involved there. With that extra tension, the two cables basically pulling against each other, one to the left and one to the right.